Thank you. So welcome to the seminar of the SONI Astani Department of Civil and Environmental Engineering. Today is our first seminar of the year, but it's not going to be the last. Believe me, we have for you quite a good series of seminars forthcoming. So our first speaker, is actually graduated from an excellent school. Maybe I'm not objective. He graduated from, guess what, USC. His name is Sharid, AMIRI. He is a senior transportation engineer at the California Department of Transportation, also known as Caltrans. Let me see, he graduated a few years ago, only 2 years ago. And his area of research was earthquake response of bridge pile foundations. His advisor was Dr. Jeff Martin, I believe. I was lucky to be on his Ph.D. dissertation committee. So I think I know what he's going to talk about today. He has been involved, and that's what he says, with mega projects through Southern California in design and constructions of major highway projects. He's a member of the American Society of Civil Engineers. He's a registered civil engineer with the state of California. He's a member of Caltrans Deep Foundation Committee, an affiliate of Caltrans General Earthquakes Committee, and Caltrans Post-Earthquake Investigation Team. You should be in New Zealand then. He's active with the Transportation Research Board, known as TRB. And is also active on a particular committee which is called Bridge Seismic Design and Bridge Foundations. So, Sharid, the floor is yours.
Thank you, Professor Bardet. Just bear with me here. Thank you very much, Professor Bardet. Thank you, everyone, for attending this lecture. And I also thank the SONI Astani Department of Civil Engineering at USC. It's my pleasure to present to you a topic that is it's a hot topic right now because we're discussing the design of our highway bridges in California. And basically, it's the acronym for it is LRFD, which is effective January 1st, 2009. And the LRFD, it's a design methodology that we're using, design philosophy that we're using that is rather new for us here in California to design our highway bridges. Stands for load resistance factor design. And basically, it's a reliability-based design methodology. And it's different from the factor of safety approach that originally we used to design our bridge pile foundations, our bridges for that matter. And the idea is to bring a systematic and comprehensive approach to design our highway bridges, both from a structural point of view and also from a geotechnical point of view. My objective for this lecture is to make sure that at least you take one thing away from this, is that why is it that we're doing LRFD, where we are on it, and where we're going with it, the challenges with it, and basically an overview of what the LRFD stands for. And that's where right now the designers in the practice, that's what we're doing. We're doing LRFD approach design methodology to design our bridges and our bridge pile foundations. I'm with California Department of Transportation. My job on a daily basis is to work on major projects and do in either in-house or oversight capacity to make sure that our bridge foundations are designed appropriately to our design standards using LRFD methods. Now, basically what we have here for LRFD is you have a situation where you have the force on one side of the equation that's being applied to your structure and ultimately to your bridge foundation components, and on the other end you have the resistance of your components to the force. In this case, when we're dealing with bridge foundations, you're talking about resistance of your soil and your structural components to the load that's being applied to them, either from a static point of view or from a seismic point of view. So that's what this is representing. And you want to make sure, of course, that your resistance are at least equal or exceeding your force effects on your components. Otherwise, you're going to have problems. Okay, now we go to the second slide. As I mentioned an equation there. That's what we have, that equation on the third bullet item. But before we go to that, let me tell you that the bridges that we're designing has to have basically adhere to some design criteria for limit states. And by that I mean, we'll get to that later on, but we also want to make sure that it's constructible and it's safe and it's serviceable. And that third equation, the equation in the third bullet item that I was referring to earlier on the left-hand side of that inequality or equation, you have the summation of your loads, and on the right-hand side you have resistance. So as I mentioned, your resistance has to be higher than your loads. Now, every single of those coefficients within that equation has a meaning. You know, the mu has a load modifiers. The gamma is the factor applied to force effects. But one word that you may want to bear in mind, it's important, is it's the emphasis on statistically based load factor. Why are we saying statistically based? And also statistically based resistance factors, which is on the resistance side. The phi there is the resistance factor. That goes to in my view, to the heart of the load LRFD design methodology. What we're doing is we're statistically looking at these elements, and we want to make sure that we don't exceed the probability of exceedance, and we want to make sure that we satisfy those limit states that I'll be talking to you in more detail later on, which is different from a factor of safety point, because as you know, when you're designing your bridge, your structural components, you used to use a factor of safety, different factor of safety for different components, be it foundation or otherwise. Now we're departing from that, and we're using probabilistically based methods to come up with our resistance factors and our load factors for our bridge components, hence LRFD. Now, the Q is for force effects, but the phi, now this phi is not the phi that you guys are using in your, a lot of people confuse, well, that's the same phi maybe we're using for soil, friction angle. That's just, obviously you know that, but that's not the case here. This is a resistance factor that we use for LRFD, the phi, and it's a multiplier that is applied to normal resistance of your piles or foundations in this case. Now, how do we come up with these resistance factors? Well, AASHTO, which is the American Association of State Highway Transportation Officials, which is basically the body that regulates and come up with the design codes for the LRFD and design of bridges nationwide. They have come up with the help from the experts with the resistance factors that they need to use. But here our emphasis is in California. What do we do in California? We need to come up with these resistance factors for soil to design your bridge foundations. We don't use a factor of safety or 2 or 3 anymore. Now we're using resistance factors to come up with this. And how do we come up with that? I'll discuss that later with you. But it's important to note that these resistance factors are different from state to state and from geology to geology and from site to site, and they need to be calibrated. And in order to calibrate those resistance factors, you need to have a lot of data in your hand, which I'll refer to later. That's probably one of the challenges that we will have. And it'll be actually an exciting thing to do. But that's something that we need, as researchers and practitioners, we need to emphasize on that we need to have more database for these resistance factors to basically more fine-tune our approach in LRFD as far as design of bridge components are concerned. Now, I mentioned limit states. For our design for bridge highways here in California and also nationwide, we're using, but mainly here in California I'm concentrating on, we're using the service limit state, which is basically, you're talking about stress and deformation, and then under service conditions. And then you have the strength limit states, which again, you're talking about stability and strength. And again, these are important because you need to basically satisfy these limit states in your design as a bridge designer, or as a geotechnical designer, or as a foundation expert, or whatever your capacity is within the industry, or as a practitioner. And of course, the last one, we can't miss that. That's the extreme events limit state, which we have here in California is mainly earthquake, but depending on which states you are, you can have different issues involved. With, you have collision by vessel, you have vehicle. Of course, we can have that here too. Ice flow is not an issue here, as far as I'm concerned. But the survival of your bridge depends on how you design that based on extreme event limit state. And in California, our emphasis is to make sure that our bridge structure doesn't collapse. In other words, under extreme event limit state. It's the non-collapse issue. So in other words, if an earthquake occurs and your bridge is sustaining some seismic load on it, you want to make sure that your bridge doesn't collapse on that. If you want to go more, then depends on which project you're dealing with, then you, of course, you do more than that. But as a minimum, is a non-collapse for the extreme event limit state of your structural, elements. Now, to give you some insight of how we design our foundations, and mainly here the deep foundations, this is basically an extraction from the methodology, from the source AASHTO guidelines and from Caltrans guidelines for designing of your bridge foundations. Basically, you're either using, your medium is either, generally speaking, you'd model it either through clay or cohesive material or non-cohesive, which is sand. And these are the methodology that you use. Now, it's important that we do use this methodology because the resistance factors that we have arrived with are dependent on these methodologies. That's another key component that we need to take with us. It's not so much that we can use every other method, but the methods that we are using to back up our design for bridge pile foundations are based on these methodology as far as California is concerned. Depending on for skin friction and end-bearing clay and mixed soils, I'm sure you're familiar with the alpha method and beta method and the lambda method, and these are the references there. If you, ladies and gentlemen, are interested in the references, I'll be more than happy to provide that to you later on after the lecture. But the idea here is that in order to come up with your nominal resistance of a single driven pile in axial compression, you need to use these methodologies to arrive to that, and that's the key for that LRFD. Of course, you have SVT method as well and CPT method. Now let me ask a question. It's kind of a common question. Does anybody know what a CPT is? Okay, good, great. I'm using a lot of acronyms here, I'm assuming, but the CPT is basically a cone penetrometer test that it's being used in the industry extensively to find out what your subsurface conditions are. Basically, it's a truck-mounted equipment that you have, which is connected to a laptop, and you go to the site, and that brings you a soil behavior profile of your subsurface conditions, which ultimately help you with design of your bridge foundations. That's what the CPT stands for. And now going after the second type of foundation is drill shafts. Drill shafts is another type of foundations that are more and more are being used in California to support our bridge structures, as opposed to the drivel pile foundations that I was referring to. Drill shafts are basically, as it's clear in its definition, its name, you're drilling a hole before building your pile, as opposed to driven pile when you actually drive the piles. And these are the methodologies that are used to come up with the capacity of drill shafts. Now, why are we using drill shafts more and more, one may want to ask. One of the reasons in my mind, in my point of view and point of view of a lot of practices, because for one thing, drill shafts, you can fabricate and make them larger as you can. You can build them and they can take a lot of loads. They can take a lot of demand. And that reduces the number of the driven piles or so-called other small diameter piles, because you can use a large diameter shaft to take a lot of loads and replace a lot of driven or small diameter drill shafts. And why do you want to do that? Well, in Southern California especially, or even in California for that matter, we are very much challenged or constrained on environmental aspects of our projects. So for one thing, when you're designing and you're building it, when I mentioned constructible, you can design it as a practitioner, but you have to make sure it's constructible too. That would reduce the blueprint on your site when you're reducing the number of piles. And drill shafts definitely would be a favorite type of foundation for that thing. Second thing is it takes a lot of demand. It can take that, and on the structural side. So from a structural point of view, it's a much more superior type of foundations, depending also where you use it and how you use it. But that's mainly the two things that you want to use. You want to reduce the number of piles, and also you want to make sure that it takes a lot of load on it for the design of your bridge. Hence, you use drill shafts. And you're using only and reese. Again, these are the methods that we do use for LRFD that has to be used to come up with the capacity of your piles. Now, this is another topic that I think it's important to discuss, and I included in my lecture, and that's pile load test, its significance and why we're doing it and where we're going with it. It really directly relates to LRFD in the sense that when you want to design a pile, you don't know always how it performs in the field. So you have to monitor that. If you don't want to use the word monitoring, you want to use other words, but however you want to sentence your wording, you want to find out how much these piles are taking. Now, LRFD guidelines in California requires that if you have certain diameter of piles and larger, in other words, it's about 36 inches or higher, then you need to have some sort of a pile load testing. Now, what is a pile load test? Pile load test is you design your piles based on those guidelines that I just referred to in previous slides, but you don't know how that, but you need to test it out in the field. And that's where you do the pile load testing, to find out exactly how your pile performs. And based on that, you can calibrate your resistance factors, which I mentioned earlier, your fee factors. Now, one thing that you also want to remember from this lecture, if nothing else, is that California guidelines is not exactly the AASHTO guidelines. We have taken the AASHTO guidelines from a national level, but we amended it with our own, at the state level, with our own guidelines. Hence the California amendment to AASHTO LRFD guidelines for not only pile load testing, but also for design of deep foundations, for our bridges, and even for design of our bridges. So we have a California amendment to that AASHTO LRFD guidelines, which is about the year 2008, those amendments, end of 2008. It was finalized. And the LRFD guidelines is 2007, 4th edition by AASHTO. Now, I mentioned the calibration for resistance factor is very important. Right now, we're using a resistance factor of 0.7 in California for the soils, for basically piles. That could change depending on if you do pile load testing or other sorts of monitoring. But that's what we use purely on design. Our hope and our goal is to calibrate these resistance factors by performing more pile load tests and other methods to find out exactly what those resistance factors are, and then apply that resistance factors to our pile design. But at the current time, it's 0.7, which is, by the way, different from AASHTO guidelines. Now, it's actually higher, which means your piles will be potentially shorter. And again, it's not final, but based on my interaction with other DOTs, Department of Transportation nationwide, every, North Carolina have some experiences with LRFD, other states as well. I'm sure they all have effective a few years back. When you use the resistance factors based on AASHTO guidelines, you are likely to be on the, in my view, to be over conservative. But then again, it depends on project site and geology, where you are. If you're on the coastal side of North Carolina, if you're not, if you're within the other areas. My experience in California is that right now we're trying to get more projects going, and that's what we're doing, and we're trying to do more pile load testing. Based on that, we can calibrate more and get that data, hopefully. And not only that, just by designing it and finding out how the piles perform, we can get more insight into where we are as far as LRFD. But definitely that's how we're designing it. We're doing LRFD in our approach here in California. Now, seismic design of bridge pile foundation is very important, obviously, in California because of here in a seismic area here in the nation. And I think it's very important as practitioners and also as researchers when you graduate from major universities such as USC, and then you want to move on either in the research areas or into the practice, to really know the importance of seismic design of bridge pile foundations. And with that, I'm going to go over some topics that I'm sure you heard of. I'm sure you heard of liquefaction, and you heard of lateral capacity and feasibility of seismic design. But what I want to emphasize is that when we're doing seismic design of bridge pile foundations now, because I mentioned non-collapse, you're allowing some sort of a movement on your bridge system, on your pile foundation system. That system has a tolerance. So it's key, and when you have a geoseismic hazard such as liquefaction, which basically is the loss of strength in your soil, which will ultimately induce settlement in a lot of cases, depending on which area you are for your system, it's critical that you as a practitioner or as a designer interact with your counterparts. If you're a bridge designer or a structural engineer, you need to interact with your with the geotech folks. If you will end up being a geotech engineer, or foundation, you need to deal with the structural people, because on one side you have your liquefaction potential of your soil due to the earthquake, and the other side is you have the tolerance of your structures and your pile, hence how much settlement you can take. The other thing is the down drag. The down drag is a phenomenon when you're actually having, during a seismic event, you have a settlement of the soil, and the crust on top of the soil, which is non-liquefiable, comes down and drags the pile down with it. And that induces extra force on your pile that could happen. And that's something that you need to design. So those are the things that is important for you to be aware of. And interact with the parties to make sure that your structure has the capacity to tolerate that. And the other item that I think I need to add to this discussion is the lateral capacity of bridge piles. A lot of times people are discussing the axial and the uplift capacities of your foundations. But more in California, we deal with lateral capacity as well. And not that in other states they don't, but here, because of the seismic zone that we are in California, your piles are bound to have forces exerted on them due to the seismic event, and the lateral capacity of those piles are very important. And speaking of lateral capacity, those drill shafts that I was mentioning to you as the largest diameter size, large diameter drill shafts are important also not only from an axial capacity point of view, but also from a lateral capacity point of view. And I mentioned the no collapse, that is important, that you don't want to allow collapse whatsoever to any of your bridges during a seismic event. That is the design philosophy for seismic design in California. You don't allow collapse. You allow movements, that subject to negotiation with to see how your system responds, but you do not allow whatsoever a collapse of your system. And your design philosophy is based on that. Speaking of piles and foundations that are in my view, have an excellent response to seismic and liquefaction and otherwise, is the KISS pile. KISS pile is the type of pile that we use in California to, again, use it because, and I'm sure the other states, depending on how they want to use it, but in California, mainly in my projects, I've been using quite a lot of it. As a matter of fact, we're going to be using some right in next 3 years in Orange County, is KISS piles, which are basically, these are cast-in-place steel shell pile. So what you're doing is, these are the piles which has the outer shell, steel shell in it, basically. And what you're doing is you're driving these shells in, right? But then you have these robust system of lateral capacity that can take the demands, because you have the steel outside that's very stiff and can take the demands and of the seismic and maybe even movement of the soil on that, which is a lateral split, which is another geohazard that could happen in a seismic zone. And of course, large diameter shafts have excellent capacity from a seismic design of bridge pile foundation point of view. Now, what are the challenges ahead? Challenges ahead, in my point of view, is that we need to have extensive field tests. I mentioned the resistance factors and how we come up with those numbers and 0.7, and they're based on some calibration, but they're not really based on extensive calibration out in the field. By extensive field tests, like for bridge pile capacity, is required for calibration of resistance factors. The challenge into that is that you need to have you need to basically, as a practitioner or as a professional in your field, structural engineer or geotech for bridge, you need to sell that concept to the owner that you need to have these testing out in the field. Sometimes they may not want to do that just because of, if it's not required, why are we doing it? Are we doing it just because you want to calibrate and get more data, or are we doing it because it's, so you need to sell, basically explain to them that that's critical for calibration of your resistance factors, and ultimately it's cost effective at the end of the day, and you give a much more efficient system as well. And then potential for overly conservative design for piles, hence more cost. By that I mean, if you're using very low resistance factors, the gentleman was mentioning where we are on that resistance factor. If you use a low resistance factors, you get longer piles. You get longer piles, they could be overly conservative and can add to the cost of your construction. Typically, if you have well, let's put it this way. In the project that I've been dealing with, the cost of construction could be from 10% to 15% to 20%, sometimes even 30 to 35%. That's on the high side. But that could happen in some cases that you have a construction of your foundation as a percentage of total cost of your structure. So it is important that as designers and practitioners, you're keenly aware of the importance of how you want to design your foundations based on those resistance factors, and hence have a very efficient system, and also bringing your cost to acceptable level so you can manage the project. So that, again, it goes to the heart of that LRFD design approach. And nationwide, we're doing calibration of these resistance factors depending on the regions and where we are. In conclusion, I want to say that the LRFD is basically a probability-based design. That's the cornerstone of the LRFD design. It's a logical extension of the LFD procedure, which is the load factor design. And by that I mean that it recognizes that there is variability in loads. Okay, so it extends that idea. And it explains how variable the loads are. And so LRFD recognizes that. And also, it will give us, in a way, a more rational and systematic way for selection of loads and resistance factors. And I think it's also important to realize that we're now bringing the entire system together. Now we're looking at the system response, the bridge, superstructure, and foundation together. The geotech and structures are kind of interacting a lot more in LRFD, which is, again, another key component of designing bridges. We used to kind of look at geotech, you deal with foundations, bridge structures, you guys with this, and then now it's a much more interaction going on, and it's required that we do interact amongst ourselves to design the bridge components of the system, and mainly at the foundation level by using LRFD, and that requires a lot of interaction between geotech professionals and bridge and structural professionals. Last one, I want to show you this picture. Is interesting. I worked on this project a few years back. This is kind of prior to LRFD, but it just shows how urbanized area we are living in, and what this is SR22 Projects. This is actually the first design-build project on a state-owned highway in state of California. It's a SR22 Phase 1. We called it, and it's a photo that I took from the project. Basically, it was given. I didn't take it, but I have it from the project, and it's a demolition that's happening on the 22 southbound I-5 connector structures. As actually, when you go into Orange County, it's very close to Irvine, like not too far, maybe a few miles north of Irvine. So you can see the demolition, that whole connector structures there to replace it by a new one, and a lot of efforts went there. It was a so-called a mega project. Typically, if it's over 100 or 150 $1 million, I think it's called a mega project. This project was over $400 million. So replaced about 35 bridges, or widened or replaced in Orange County. I think that's the end of my presentation, and if you have any questions, I'll be more than happy to answer.
I've been coaching the questions. So do we have any questions I'm going to take the microphone, and we're going to pass back and forth the microphone, because we are recording here on this video camera, and you can see actually yourself on YouTube in the short future. But we noticed that we need to make sure we have the microphone so we can get the sound in the camera. So do you have any questions for our speaker? Yes.
So LRFD is essentially a force-based design, right? It says we have certain forces being applied to our structure, and we have certain resistance to those forces. But in seismic events, that may not be necessarily the relevant factor. You may have an energy requirement. You may need to absorb, you know, a certain amount of energy. You may need to, you know, prevent some crack from opening more than a certain amount, something like that. Especially maybe at joints. And, you know. So how do you incorporate requirements outside of force-based requirements within an LRFD?
Well, I guess the question you're asking, I was asked to repeat the question. You're asking is how do you incorporate in LRFD the situations where you don't when you have cracks and when you have displacement of your structures, and you're assuming that's a force-based design approach. Answer to that is that LRFD, it's not a matter of being a force-based design. Actually, in California, we're departing from force-based design. What we've been doing, mainly, it's a displacement. We allow displacement, and that's what I was referring to in the, you mentioned earthquake extreme event, which is an extreme event. We allow displacement, as I mentioned, settlement is sort of a displacement. We allow displacement and ductility in our system. Now, we don't allow our piles typically to go, to go inelastic. That's the approach we've been doing so far. But again, project that could be different. In some piles, like pile extensions, that may not be the case. But again, it's we do allow displacement, and we do allow the ductility of the components to take that energy of the earthquake and absorb it and take care of it. And mainly in foundations, we don't allow and one of the main reasons we don't allow that kind of a basically to piles to go inelastic during an extreme event is because the explaining is that we don't want to go and dig the ground and go inside and see where the damage is. But I think there is also some discussions on that they're allowing ductility and obviously ductility in piles. That's in the latest seismic design criteria as well. So, answer to your question is we do allow displacement and ductility in the system. So it's not purely a force-based design as you mentioned.
The equation though is essentially a force equation, inequality. Or are you also allowing displacement?
No, the equation, if you had a look at the left-hand side, you have the new, which is the, you allow the ductility into that. I don't want to go into the detail of it, but yes, you do have ductility into your equation. That ductility allows displacement of your components, and therefore, it's not a force-based design. Yeah. Force is on one side of the equation, but then you have the other side, which is the resistance, which goes into the ductility of your system as well. I don't know if I answered your question or. Yeah. Okay.
Well, if I may, I have a few questions. The first one is you showed three kinds of criteria, right, for the bridges, from the basically a no collapse to serviceability, and then to moderate damage, basically. Now, this must apply to some categories of bridges, right? Because as you look at the criticality of the bridge within the network, you have maybe to put some factors on this, whatever, the three different criteria. Some bridges, you don't want them at all to be damaged after an earthquake. They are critical bridges, right? You want them to be usable right away. And so some of them you can maybe tolerate a few hours of delay, right, after the earthquake. And none of them, of course, you want to collapse. But so how do you account for this criteria of importance? You have to come up with a matrix now, right, where you expand your 1, 2, 3 criteria into some other dimensions to account for the importance of the bridge. So how do you do that?
Well, that's an excellent question, Professor Barde. What I mentioned, no collapse. That was a minimum, the threshold. In other words, we don't want our bridges to collapse during a seismic event. Now, as far as how do we categorize our bridges at the level of importance, there's a whole bunch of folks in Sacramento whose jobs are just to categorize bridges based on their, based on how important the bridges are, based on their functionalities. And they categorize those bridges, like important bridges, critical. Toll bridges are important bridges, they're critical. So there's a different seismic criteria for that. Ordinary bridges, the one that I was mainly referring to, were the ordinary bridges and highways, that there's some other criteria. Now, we also design bridges, like you mentioned, a 2-level and that's very important to mention. The two-level earthquake design, which is one is functionality and the other one is collapse. So depends on who the owner is. For example, in a project in Orange County, we had two-level design. One is, as you mentioned, no collapse, and the other level, which is even more stringent, is to make sure that you have functionality in your bridge. You don't want delays in traffic and the bridge closed for a long period of time. That again, it depends on if you're dealing with the owner, with another external agency who owns the road. Maybe it's a private road, but it could be a state road later on. Depends on that. If you're, let's say, working on the ports, there's some projects at the ports they have that level of seismic design as well on the bridges close to there. So it depends on how you want to design it. But what I was emphasizing in this lecture is, or presentation, is mainly how we do as general for our ordinary bridges, which is basically where the seismic design criteria for Caltrans stands for. The STC, so by the way, seismic design criteria, which is a guideline how to seismic design our bridges in California, refers to the ordinary bridges. They don't refer to the important bridges, toll bridges. They refer to the ordinary bridges. And that's what my, which is 99% of, as far as number of our bridges are those, more or less. So, but the answer, how do we categorize those and which method do we use and what metrics do we use? I am not personally aware of how they come up with that. All I know is these are the categories and how we have to. But I'll be more than happy to come up with an answer, or maybe send you an email and see how they actually come up with this. But that's in the STC as well, and the guidelines in the Caltrans. That's how we actually come up with the exact way of dealing it. Obviously, toll roads are critical because of the importance of the bridges, the size of it, and the structural components of it, as opposed to ordinary bridges, which are using it on the on your daily traffic. But important, we don't mean the ordinary bridges are not important. They're also important. If, let's say, your bridge is within a toll road, that gives another level of importance, in the sense that you may need to have another seismic constraints on that as far as design is concerned too. So, or if you're getting close to a hospital or something, depends on who the owner is and how they want to design that. That also has to play some role in it. And that's an evolving thing as well too. So it's subject to change.
Do you have any questions for? Because I have another one for him. Actually, I have quite a few. I can detain you until 4 if you like. So the question is actually on what we call frigidity curves. When we assess the vulnerability of a network, we use usually frigidity curves or vulnerability curves. They tell you basically the probability of failures of exceeding whatever when you exceed a certain threshold. It could be a displacement threshold. So are we going to get from you, from Caltrans, fragility curves for your bridges? In other words, when you run your analysis, you do it for design, a particular design, a system of loads, right, to assess the earthquake forces. Are you running, pushing your analysis far beyond that particular design loads to see how well your structure perform when you exceed the design? See, my question is, are you actually testing things to see how the structure behaves far beyond the design load?
I guess, again, another excellent question. I think from a practitioner point of view, Professor Bardet, if you're asking me, am I doing that? No, I'm not doing that. I'm designing my bridge pile foundation based on the seismic event that we think is going to dictate the criteria. So that's what we're doing. It's going to be a spectrum of earthquakes, because right now we're moving toward probabilistic approach. As far as, it's deterministic and probabilistic combination of the two right now in Caltrans. So if you're saying, are we exceeding that and we're going to look into that, we're not doing that as far as I'm concerned. However, you mentioned fragility curves. I know and I'm aware of a lot of research and work that's being done in collaboration with Caltrans to discuss the fragility, not only in California but in other states, the role of fragility curves in the system response, and even in the geotechnical aspects of bridge foundations. For example, fragility curves are being addressed on the scour issues for bridge pile foundation during a seismic event, or other issues, or lateral spell loading on piles, or how vulnerable our bridge foundations are or the systems are during a seismic event as a system using fragility curves. So that has been done at a research level, I'm not sure if it's been incorporated fully in a practical level from a geotechnical point of view. Not that I'm aware of in my projects, which are for the past years. But is it something that is being discussed in Caltrans actively at the yes, it is. Are they in touch with the other universities? I'm sure they are, because I've been in coordination with them and I've seen these results and analysis. But I'm not sure how far they've gone into the practice. As far as the practice part of it is concerned, here in Southern California, I haven't used fragility curves, nor have I seen any consultants on the consultant side to use that to come up or calibrate the bridge foundation response during the seismic event.
Any more questions? Well, if not, we're going to close the seminar. It was our first seminar. It's going to be a short one, but sometimes short is good, right? So I'm going to close the seminar, and I want to thank you very much for your time. But first, I think we should thank our speaker. Thank you.
Thank you.